All right, let's have a quick conversation about transformations. And we only have a couple slides, but we'll still probably take almost 20 minutes to do this, maybe even the full 20, I don't know. But let's dive into it. So most of the time we do really well with transformations, but there's a little hiccup. Some of us have a little bit of trouble when we talk about the stretching and compressing. All right? And I know why it's confusing, and I'm going to try to break it down for you so you can make sense of it. So, first of all, the negative, we all do really good with that. And actually, before I even get into that, tip for you. I always take the variable and say, what's happening to the variable? In this case, it's being squared. Now, because it's being squared, I know this thing is roughly behaving like x squared. So, not a super common terminology, but we call it a parent function. And the parent function for this graph is x squared. So whatever this graph does, it's going to look something like x squared. So parent function's x squared. The graph I have over there on the left, that's its child, right? And so that helps you kind of envision what's happening. So whatever's going on, it's going to look like x squared. So if I go over to Desmos, I have x squared graphed here, and right, that's a parabola, that's a U shape. Hopefully you remember that. If not, that's in the next units, right? Or the end of the linear and quadratic stuff. But whatever this graph looks like, it's going to look similar to this, okay? All right, now let's go back to breaking it down. So if there's a sign out in front, that's a flip, and if it's negative, that's a flip over the y-axis. Not y-axis, x-axis. Okay? Most people get that, they do good. Now, here's where we start screwing up. So, a lot of people get this wrong, but then still get it right. Okay? So, the 3 there is actually a vertical thing. And here's how you can think about it. You give me x, and I do my stuff to it, square it, and then I multiply by 3. So I'm multiplying by 3. In other words, the output is getting multiplied by 3 after I've done the squaring thing, after I've done the parent thing, right? And so because of that, I'm changing the outputs, the y values, by 3. And so this thing is going to grow 3 times as fast. So actually, if my number is between 0 and 1, oops. All right. Now, when I say my number, I mean ignore the sign. Ignore the negative, because the negative is about flipping. So that number up there is a 3. Okay. If I have a number between 0 and 1, that is actually going to compress my graph vertically. So squeeze it down vertically. If my number is greater than 1, then that is going to stretch it. So let me try to convince you of that. Okay, so if I come over here to Desmos, and if I have x squared, I could type in 3x squared. All right, let's change the color on that. Maybe, let's try, I don't know. Maybe I don't need to. Oh. There we go, blue, aha, genius. So you can see compared to the red one, this thing is skinnier. Now, we have a tendency to incorrectly, but yet kind of correctly, we have a tendency to go, oh, well, horizontally this was compressed. While visually that's accurate, mathematically that's not what's happening. Again, what's happening is, my outputs, instead of being here, it's 3 times higher. So my vertical outputs are growing 3 times as fast. Or in other words, you could think about, hold on to that vertex, grab the top of the graph and stretch it up. So it's a vertical stretch. Okay. Now again, if I said there's a number between 0 and 1, so let's take 1/10. Well, my outputs are growing 1/10 as fast. So they're growing slower compared to my parent function. And so you can see that, therefore, it's getting compressed down, making it wider. Again, some people will mistakenly say, oh, the 1/10, or the 10% out front, that's making it a horizontal stretch. No, it's actually not horizontal. It's a vertical compression. Okay? So that's actually super important. And you'll see why on the next slide. Now, we do pretty good on the rest. Most of us were good. We know that the inside part, that's a left-right shift, and we know they're the opposites. And so if that's a -4, that's actually shifted to the right 4. And then we know that whenever we add or subtract something on the end, that's an up-down shift. And we know that this thing is being shifted up 5. So great, we nailed it all down, we got it. So if I came over here and did this thing in order, it's minus, there's my flip, right? 3, there's my stretch. Now we're going to move it to the right 4, and now up 5. And there you go. So I know it's been moved to the right 4, it's up 5, it's flipped, so I know since parent function's parabola, the parabola is going down, and it's a 3, so it's 3 times as fast. In other words, it's getting stretched vertically, so in other words, it's a little skinnier looking, if you will. All right? Great. Okay, let's go on to the next slide. Now I threw a 2 in there. Almost everything's the same, but here's where we screw up big time. And this is also why we need to know our differences here. So yes, still a vertical, or excuse me, still a flip over the x-axis. That's still vertical. We already talked about that, so I'm not going to rehash that. However, this one, that 2, so when you have a number in front of the variable inside of the function, now what do we mean by inside? Well, remember, my parent function is x squared. So it's inside the thing being squared. That's the inside of the function, then, if you want to think of it that way. If you have a coefficient on your variable inside, that is horizontal stretching and compressing. And now, again, if we have numbers between 0 and 1, again, ignore the sign. You could throw a negative in there. By the way, if there was a negative inside, that's a flip over the y-axis. I'm not going to do one of those, but that's one extra little nugget in there. Now, remember, things on the inside, just like our left-right shift, are opposites. Okay? But be careful. And this is still up-down, by the way. And that's up 5. Now, careful. You notice I didn't write how my left-right is, because there's a reason. Now, that 2. Now, this is the inside. So it's before you've squared it. So this is not about the outputs, because the 3 affected the function after you squared it. Now remember, what's my function? X squared. That's my parent function. So the 3 happens after the squaring. The 2, though, the 2 on the inside, following order of operations, we do that before we square it. So if you want to think about it, it's technically happening before you do the heart of the function. In other words, it's not happening to the outputs of the parent function after you square it. It's happening before you square it. So in other words, the stuff on the inside is actually affecting the inputs. So this 2 is making my inputs go twice as fast. All right? So it's kind of not easy to see, but if I come over here, if I say 2x squared, I guess I should do some y equals. It doesn't matter, it's still going to graph it, but that would make me feel a little better. All right. So the blue one, some of you are like, oh, well, 2, vertical stretch. It's growing twice as fast, isn't it? So isn't this the same as what we did? No, it's not, and I'll show you why. You say it's growing 2 times as fast, so you're saying it should be the same as this. And you notice it's not. Why isn't it? Because this is on the inside. So that square also affects this too. So we could simplify that, and technically if I worked that out and simplified it and all that, actually you would get what? That blue one is the same thing as y equals 4x squared. Whoops. Not sure what happened there. And now you can see the purple is overlaying on top of my blue. So actually this 2, in some ways, is really a vertical stretch of 4 effectively. But that's not really the proper way to think about it. Here's how you should think about it. Because it's on the inside, it's causing me to double my inputs, or in other words, get through my inputs faster. Well, if I'm getting through my inputs faster, the red graph's the original graph. You know, so when I plug, well, twice as fast. So let me zoom out. When I plug in 1, well, because I'm going twice as fast, it's actually treating it rather than, well, you're not plugging 1 in, you're twice as fast. So it's actually the equivalent of plugging 2 in, which is 4. Which you notice on the blue graph, when you plug in 1, it's the same thing as when you plugged in 2. All right, or the other way, just you're going twice as fast. And when you go twice as fast horizontally, that's going to squeeze your graph down because your graph's moving faster. So actually these are opposites. And so if my number, if my number is bigger than 1, I can do this. Then that is actually going to compress it. It's opposite. It's opposite of what we talked about with the verticals. And if I have a number between 0 and 1, that's actually going to stretch it. All right, so let me try to prove that to you. Go back over here. So 2x squared, the blue one, it's the 2 is bigger than 1, or bigger than 1, and so horizontally it's compressing it. So now let's do a 1/10. But again, it's on the inside. Oh! So actually, that thing got super wide because opposite, it's actually stretching it horizontally. All right. Okay, so when it's on the inside with the variable, that's actually horizontal, and it does the opposite. Things on the inside kind of do the opposite. All right. Now, last but not least, some of us would want to say, oh, this is a right shift of 4, and you'd be wrong. Here's why. Because when you have that 2 in there as a coefficient, you have to factor it out. And so if I was to factor that out, this would turn into what? That would turn into f of x equals -3 times 2, and then I'll say, so when I say factor it out, I want to factor it out of this inside stuff. All right, so there, now I've isolated the horizontal stretch compression. In this case, a horizontal compression. But when I isolate it, I then get that. So now my left-right shift is to the right 2, not 4. So let's see it in action. Let's go back to Desmos. So y equals -3 2x minus 4 quantity squared plus 5. And now you can see it is thinner, but it's thinner. It's thinner, well, first of all, because it was vertically stretched, which causes it to get thinner. But then on top of that, I have a horizontal compression that's making it even more thin. To convince you of that, so see, without the 2, the purple one is thinner than the red one because of the 3, but the addition of the 2 compressed it horizontally even more, so this black one is even thinner than this purple one. Okay, so alright, so see, not lying to you. So we kind of get this double effect here going on between the 2. All right. Now, furthermore though, it's not to the right 4 and up 5. That's not where my graph is. So like I said on the other slide, we actually factor this out and you get a -2 when you do that. So actually you notice it's over 1, 2, up 5. So that does correctly describe where that thing lands. All right. Okay, so hopefully that helps clear up this idea between vertical versus horizontal stretching and compressing. And then the beauty of this translates across all functions, and that's part of like learning the course. So for example, we haven't learned exponential functions yet. We will, but it doesn't matter. You should still get it. So I'll tell you this, exponential functions are functions like e to the x. E is a number, 2.7 and change. So just, similar, it's a similar equation like 2 to the x power, right? But e is a special number like pi and other things. All right, so anyhow, so my parent function is e to the x, and then if you're not aware, e to the x actually has a horizontal asymptote on the left and then grows exponentially faster and faster and faster as we go to the right. So I know this function is going to look something like that. But now, what's going on with it? Here's what's going on. That's going to be a flip over the x-axis. This is on the inside of the function, right? So I do know technically I should rewrite this if I want to get my transformations right. All right, and so therefore, 3, that's a vertical stretch. The 2 is what? That's horizontal. Remember, it's opposite, so it's not a stretch because it's a 2 and it's in the inside. That's actually horizontal compression, right? So it's squeezing it in horizontally. And then this thing is going to move to the left 2 and then up 5. So even though you don't really know a whole lot about exponential functions, or maybe some of you do, but we haven't learned them yet in this course, you totally should know what's going to happen to that function, roughly speaking. The same sort of principles apply. And let me just prove it to you. Let's go over to Desmos. Let's look at the graph and convince you it works. So e to the x. Nope, that's a 2. E to the x. There we go. So there is that asymptote on the left, and then starts growing faster and faster. Okay, so here we go. So again, if I just did the negative, that's going to see that flipped it. If I add the 3, hard to see. It is getting it's actually a little, here, I'll convince you. If I take the negative off, you can see it's growing a little faster, right? So there we go. So I got a little stretch there. Okay. The +5 definitely is moving it up. So see how that moved it up. So +5, here it is. +5 moves it up. All right. Now up here, if I do a 2, it got a little thinner. See, right? See that horizontal compression on there? But this is 2x +4. All right, so there we go. And so the +4 actually moved it to the right, if you noticed that. If you didn't catch that, +4. See, moves it to the right. Okay. Awesome. All right. So that's kind of the idea there, and then we could take this one step further. So you'll see some books when we talk about these transformations. So like if we take x squared, you could think of them as a bx plus c squared plus d. And then each of those a, b, c, and d all affect the parts, right? So the a is your flipping and your vertical stretching or compressing, right? Your b is your horizontal stretching or compressing. Your c is your left-right shift. However, be careful, factor out your b first. And then your d is your up-down shift. Now, if I have an exponential function, a e to the bx plus c plus d, right? A, b, c, d still have all the same effects, right? What if I'm working with an absolute value function? A absolute value of what? Bx plus c absolute value plus d. They have all the same effects. Parent function's absolute value, it's a V shape. The a, b, c, d all play the same roles. Later we'll do trig. A sine of bx plus c plus d. A, B, C, and D all have the same effects, right? And the parent function's a sine function, so it's going to be shifting it in the same exact kind of ways. Again, same thing here though, and here, if we're going to talk about our left-right shift, make sure you factor the B out, right? So like we did up here, we factored this 2 out, and so instead of a left shift of 4, it's actually a left shift of 2, right? So always got to factor that B out to get your correct left-right shift. But again, all sorts of functions, whatever their quote parent is, when we talk about these left-right, up-downs, compressions, all that, all these things work. But you got to be careful. You got to be able to distinguish between the horizontal and the vertical, okay? So I hope that's helpful. I hope that kind of clears up transformations a bit and kind of helps you navigate the rest of the course, because this is something that's going to come up over and over and over again, because it's kind of a big topic. All right. With that, I hope you have a good day.